Good morning to all of you. Today we'll discuss the shunt compensation 2 review. That is different shunt compensators, which includes thyristor control reactor, thyristor switched capacitor, and thyristor control switched reactor, and combinations of this one plus statcom. Just we discuss the review of unit 4. Unit 5 is about series compensation. Unit 6 about unified power flow controller. Now we discuss the review of unit 4. So this unit 4 is about shunt compensation, that is 2. Shunt compensation 1 is about objectives of shunt compensation. Now we discuss the review of the actual different components in this shunt compensation. Okay, so I will list out one by one. So here, as per syllabus is concerned, first we have thyristor switched capacitor. As per syllabus I am saying. Actual order, okay, that you will have TCR, TSC, TSR, TCR, TSR, and TSC, and then combination of TSC, TCR, and then STATCOM. So that is the actual order. But as per syllabus is concerned, we have TSC, then TSC, TCR, and then STATCOM. So that is about syllabus is concerned. Then third one is about STATCOM. So these are the different shunt compensation available in the fourth chapter. Okay, I will explain one by one. Okay, first of all, the shunt compensation is classified into two categories. One is a variable impedance type, and the second one is a switched converter type. The meaning is there in that classification itself. Here the impedance is varied, nothing but reactance of this one is varied in any of these devices, whether it is connected in series or shunt. This is the classification you are considering. In that case, the characteristic impedance of the transmission line is varied by connecting an impedance either in series or parallel. Once if you connect directly in series, then reactance will be either increases or decreases. For example, the transmission line is inductive in nature. So once you connect a capacitive reactance, then the reactance will reduce. Once you connect in again inductive in series, then reactance will increase. But we don't want the reactance to increase. We require less impedance so that drop will be less, and other advantages we get because of this one. So here one type of classification is variable impedance type synchronous generators or synchronous compensators. Okay, next one, the switching converter type. We use same to get properties of capacitor or inductor. We use the STATCOM. Okay, so we'll discuss one by one. This is actually the review. So first we'll discuss TCR. So this one we are discussing first, that is thyristor control reactor. Then we discuss thyristor switched capacitor and combined TSC, TCR, and then STATCOM we discuss. So for any circuit, we require a power circuit diagram. Whether it is a FACTS controller or power electronic subject, we require the power circuit diagram. So here, what is the TCR? Okay, TCR is a shunt compensating device, and it controls the current passing through the inductor by using switching. So in this one, in this TCR, thyristor controlled reactor. So we have reactor and a switch. Number of times I told in case of AC switch, okay, we have two devices, switching devices connected anti-parallel, whether it is a thyristor or a GTO or any other switching device. If you take, we connect in anti-parallel. So that is taken as a switch or valve number of times, because one is acting in positive cycle and other is acting in negative cycle. So this is taken as a thyristor valve or switch, that we represent it as a SW switch. Okay, so that is a switch, AC switch, and connected to the ground, and this is the transmission line, and it is maintained at voltage V, and current passing through the inductor we take it as I. So this is the power circuit diagram of a thyristor controlled reactor. First device, though we have syllabus as a TSC, TSC, TCR, STATCOM, generally we have this TCR first. Okay, then, okay, then second one, thyristor switched capacitor. Here itself, I am representing the diagram, that is thyristor switched capacitor. Okay, please go through this one. We discuss thyristor capacitor. Same, you can see that here, just I am replacing the inductor by the capacitance. Circuit, remaining power circuit diagram is same. Okay, that means we have the uh, in capacitor in place of inductor. So this is the power circuit diagram as per thyristor switching, thyristor switched capacitor is concerned. Okay, so this is about the thyristor switched capacitor, but small modification we have. So that is here a small inductor. Okay, inductor is connected here, a small value. Okay, very less number of turns you can represent. Here it is connected. What is this actually? The main function of this is a TSC. The main function of this is done by the capacitor, not the inductor. Then what is the purpose of inductor, that we will see. Okay, so but in this case of this thyristor control, this is a TCR power circuit, thyristor control reactor, or this is same as a thyristor switched reactor. This is the power circuit diagram for either thyristor controlled reactor or thyristor switched reactor. Okay, this is the power circuit. And for the other one, that is for a TSC, this is the power circuit represented in green. Okay, and here small value of L inductor is connected in the circuit to limit the current passing through the inductor whenever malfunction of switching takes place. Under normal condition, it won't have any effect, but whenever okay, whenever if you want, okay, whenever if you want, okay, to reduce the current under abnormal, that means the capacitor case is completely different. Whenever the malfunction, okay, or switching at unwanted time gives rise to transients, which is injected into the power system, and again the power system may be damaged because of this one. So okay, not only this capacitance and this switch, power system is also damaged because of these transients. So to limit any transient currents produced due to malfunction of this switching, we use inductor. And also one more purpose is also stated here, to avoid the resonance condition with the supply. Okay, because generally the switching on of the capacitor will create resonance condition. That is also a problem. Because of this resonance, you get currents that again damage the power system, because this capacitance in series with this line inductance may form the resonance condition. To avoid that one, we use this capacitance. That is also the other purpose. Main purpose is to limit the current. Okay, so this is about the thyristor switched capacitor and thyristor controlled reactor and thyristor switched reactor. Okay, and combined we use combined one also, that is this one. So if you draw both, then it becomes a TSC TCR. That's nothing more than that. Actually this TSC TCR will have these two, that is thyristor controlled reactor and thyristor switched capacitor. This is designed to reduce the standby losses in the case of FCTCR. FC means fixed capacitor. Fixed capacitor, thyristor controlled reactor we have. Okay, but that we don't have in syllabus. So we need not, but while you are discussing about this TSC TCR, we should know about FC TCR. FC TCR means the same thyristor controlled reactor. Okay, with we have permanent capacitor. Okay, switched, fixed capacitor switched on. So this is TCR circuit, and this is permanently switched capacitor. In this one, we have disadvantage of standby losses. That is, whenever XL is equal to XC, even during that condition also, you will have the losses. They are called standby losses. When XL is equal to XC, it won't have any function to do, because it neither absorb reactive power nor supply the reactive power once they are equal, because they are cancel each other. Then even at this condition also you get the losses. To rectify that losses, actually this TSC TCR is proposed. So that's why we are discussing one point related to FCTCR while discussing about TSC TCR. So these are the power circuits for all. You can see that TSC, TCR, TSC, TCR, all these one. So here all are covered. Okay, power circuits are concerned. Okay, then we'll discuss the next operation, waveforms and other. Okay, so first of all, the shunt compensators. I'm repeating, shunt compensators are classified into two categories. One is variable impedance type. In this case, the capacitors or inductors are used along with the switches, thyristor switches, and all these are placed in parallel to the transmission system. When it is placed in parallel or series, the characteristic impedance of the transmission line is changed, so that the impedance is changed. That's why these come under that category. Other one, that is a STATCOM, we don't use directly these capacitors or inductors. We use switches, nothing but converters. We use converter, either voltage source converter or current source converter, and we make the current either leading or lagging. Same as in case of a synchronous machine connected to the infinite bus bar or synchronous motor, or excited, under excited, depending on that excitation, the lagging or leading current nature will be different. If it is under excited, then the generated voltage will be less than the terminal voltage, and if the over excited E is greater than V, based on that one, the nature of the current lagging or leading present. So that we have discussed. So to know that basic STATCOM operation, first we discuss a synchronous machine. Okay, synchronous machine. Synchronize it to infinite bus bar. That means you can take it as a synchronization experiment in the case of machines, or V and inverted V curves of synchronous motor. We do experiment separately. So that also you can consider. Both anything you can consider. Both. That's why we call it as synchronous machine, not as a generator or motor. Depending on the condition, it may act as a generator or motor. So it is a synchronous machine. The excitation is very important. Generally the excitation will be changed by changing the field rheostat. That is depending on the field current. Once you increase the field current, then excitation, that is E, will increase. The once you reduce the field current, that is excitation, then E will reduce, then the terminal voltage, then current lagging takes place or leading takes place, depending on that E and V magnitudes. Then real power, once in a synchronization experiment, we'll go back to the fundamentals and we discuss some of that related to that one, and we come back with this again. Okay, please wait. Okay. So in the case of synchronous machine, synchronized experiment, synchronization experiment, if you see that we make the voltage equal to the terminal voltage and frequency is equal to the that frequency of the supply, and phase sequence we make it as same as that of the board that is in grid power supply, and then we close the synchronizing switch. Once the machine the synchronized alternator is synchronized to infinite bus bar, then even if you change the excitation or the field winding of the motor, that is input, once you change the mechanical power or the excitation, the speed and the speed and the voltage won't change, because that is synchronized to infinite bus bar. So that is directly connected to the infinite bus bar, then voltage won't change. And then the once you change the that is speed, input speed, that is input power, mechanical power, then speed won't change, frequency won't change, because it is fixed and that is decided by the infinite bus bar. Then what will happen? Real and reactive powers flow will change once you change the excitation or the mechanical input to the generator, that is the field rheostat of the motor, that is input you are changing. So real power and reactive power are changing once that is synchronized to the infinite bus bar. Real and reactive powers. How? Once you give extra mechanical power, then the machine will send the real power to the grid. Or if you reduce the field rheostat of the motor, then that synchronous machine will draw real power from the grid. And similar to that one, if you change the excitation, if you increase the excitation, then the machine will supply the reactive power to the grid. Or if you reduce the excitation, then the machine will draw the reactive power. That means it can supply, it can absorb the reactive power once you change the field excitation of the alternator, once it is synchronized. That is okay, that is infinite bus bar. And if you change the speed, then what will happen? Real power flow either absorbed or sent to the mains. So that is exchange of real and reactive powers takes place once you change the excitation and once you change the input power to the alternator. Either decrease, increase, or in this excitation also increase, decrease. So real and reactive powers. Okay, and here how it absorb reactive power or how it supply reactive power, that depends on excitation. For example, once just synchronized, then neither supply reactive power to the mains or nor draw, because we have taken the voltage of the alternator to exactly the same as the grid voltage. Now if you from that point if you change the rheostat position, that is if you decrease the current, then excitation will decrease, generated EMF will decrease, so that current will flow, that is E is less than V, so that it absorbs reactive power. And if you increase the field current, E increases, so that E is greater than that V, so that it supply the power to the that is reactive power to the grid. So that you have to understand. Or in similar V and inverted curves, you can do that experiment after synchronization of synchronous machine to the infinite bus bar, or separately we are doing this one in the separate experiment in the synchronization experiment, that is in the other one, that is the V and inverted curves of synchronous motor separately we are taking. Okay, so there we are running the motor first itself usually as a synchronous motor. Okay, then we do this one, that by changing the excitation, now we note down the current values, power factors and all these, and we draw the graphs between field currents, armature current, field current and the power factor, and we draw V and inverted V curve. You have to understand how the reactive power flows, that in this case you have, because you are there, in that case you are measuring the power factor clearly. Okay, that is really we are measuring the power factor using a power factor meter. There we know whether the power is inductive or capacitive. From that we can know, because the power factor meter is having both leading and lagging, and at the center you will have one unity power factor. We take all the readings. Okay, so that you have to understand, because while discussing about this statcom, we take analogous one, that is a synchronous machine, overexcited and underexcited, and how that is absorbing or supplying reactive power dynamically. Same case we are taking with the statcom. Same effects you get in the case of statcom with this, that is like synchronous machine. We get the voltage greater than the that transmission voltage, so that current is leading, so that it absorbs reactive, it supplies reactive power. In the other case, it supplies reactive power, it absorbs reactive power depending on that terminal voltage. Okay, and that is we have discussed about statcom number of times. Okay, and that is and then depending on the leading and lagging, that is voltage, that when we assume that assume that is the induced emf of these, or the terminal voltage of the statcom, and v is the supply voltage, that is the transmission line voltage, depending on the lagging and leading. So this real power phase angle, based on the phase angle difference, you get the real power flow. Once E is greater than, that is phase angle difference, if E is at leading with respect to V, then it supplies real power to the mains. Or if V is at a leading angle with respect to this E, then it absorbs real power. Okay, real power flow depends on the phase angle difference between the transmission line voltage and the terminal voltage of the statcom. So that you have to understand, because real power flow formulas we have seen. So that is the depends on the phase angle difference, though voltages are same. So that you have to understand in the case of statcom. So here all the two are coming, that is TCR, TSR, TSC. Now we'll see the operation of this one, and we move to the statcom after this one. Okay, how it operate, and how this value, that is the current, depends on the, okay, alpha, where alpha is the delay angle. Similar analysis we have discussed in the case of series compensation, that is GCSE. So here whatever we have discussed in TCR, same analysis there we have adopted for the GCSE. There capacitor we have considered. Okay, I will tell you that circuit also. I will explain. Okay, I will explain that circuit also. Okay, see. So here, in the case of TCR, thyristor controlled reactor, the current passing through that is varied by using delay angle. Okay, how? Okay, here in the case of inductor, please remember, in the case of inductor, we draw simply the voltage and currents as in the case of secondary networks. Okay, for example, here I am representing the first the voltage. Okay, voltage one phase I am representing, and current, once it is turned on, as usual, whenever, that is whenever capacity is in the circuit, you will get this type of this type. Okay, just current is lagging by 90 degrees, that's all. So this is the current value, and this is the voltage. In the case of the inductor, because inductor, in case of inductor, current lags by 90 degrees. Simply you can draw any number of times, or this one you might have drawn in the secondary network. But then how we change using this switching, this how, okay, that is important. Okay, so here in this case we are not switching on the device. That is, here we have two devices, T1 T2 in this switch, thyristor 1 and thyristor 2. Thyristor 1 is favorable for conduction in the positive half cycle, so that if you turn on T1 at this instant, you get this waveform. Instead of turning on T1 at this instant, if you are allowing some delay, you get this type of waveform. That means it will be 0 up to this one. You get this type of waveform. Again, it will be 0. So once you see the conduction angle, that is different. So this is called a delay angle. So then this is the conduction angle. So this is the conduction angle. Okay, so that is reduced. Previously it is pi value, now it is reduced to this one. That means we don't get the current full, only partial value or small value of the current you get here. Further, if you reduce, you get this one. Or here, if you have one more, for one more value of alpha 1, you get this one. So you can see that like a design that you are getting. That means for different values of alpha, you get the current, this one. And once you take alpha is equal to 90 degrees, you don't get the current at all. So that is about TCR. That means you can vary the current from maximum to minimum 0. So that you have to understand. Same analysis we take in the case of GCSE. That is when a capacitor, that is series capacitor with connected with GTO. GTO, same analysis. There only the difference is that the devices are here GTO. GTO. And here this is series connection, there shunt connection. So here this is series connection, series capacitor. This system is, this set is connected in series with the transmission line, but whereas this one is connected in parallel to the transmission line or shunt. Okay, so here the current we are considering it as okay, I, that is sinusoidal. You can see that same similar waveforms I represent again at this point. Please go through this one. Okay, so here I am representing that okay, the diagrams related to this series compensation, that is GCSE. Here I am taking first with green, I am representing the current we are taking constant. And the current is leading in the case of the capacitor. So just in place of voltage you are representing the current, and in place of current you represent it as a voltage. That's all, we represent it as a voltage. Here I'm representing the voltage. So this is the voltage as in the case of GCSE. Okay, if you turn off, please remember here, once you turn off this one, then capacitor will be coming to picture. Turn off, we are turning off these GTO at this instant, so that you get this type of waveform. Instead of turning off at that instant, once you take some angle, some delay, if you turning off, if you are taking some delay, we don't get a complete voltage waveform. You get okay, you the only partial voltage. So this way you can get different voltages, maximum to minimum. Use here, we assume it as a gamma. This angle we assume it as a gamma, that is switch off angle of this GTO. Once GTO is switched off, then only capacitor will come to picture, because once if it is on, then this will be bypassed, capacitor will be bypassed, because generally the current choose the short circuit path or the low impedance path. So instead of going through the capacitor, it go through the short circuit, that is via this switch. So that's why you don't get any voltage across the capacitor, or voltage will be 0. And if you turned off at some delay angle, okay, gamma, then the conduction angle is different, so that you can vary the voltage from maximum to minimum by using gamma. Same concept you are taking in the case of this the thyristor control reactor. So once you know either the TCR operation or this GCS operation, you can know the other one easily, just because only difference is that where one, in case of TCR we use the inductor and it is a parallel shunt compensating device. In case of GCS, it is a series compensator device. We use a capacitor and GTO in place of the switch. Okay, this thyristor switch. So that is the analogous terms, and the graphs, or that is the waveforms are just voltage and current are different and other are same. So using this one, we can control the voltage and current, so that reactance is controlled in both the cases. Okay, reactance, how reactance is taken as voltage by current. Here current is varied, here the voltage is varied, so that reactance is varied. By using that, we can get variable inductance or variable capacitance. Okay, that is about variable impedance type, the compensator, shunt compensator and series compensator. Okay, then here in the case of this TSC TCR, okay, TSC thyristor switched capacitor. Okay, already told. Okay, thyristor, in case of thyristor switched capacitor, uh, we don't have possibility to change the voltage across the capacitor. Only you can switch on and switch. Okay, switch on at the required instant, and it cannot be changed. And depending on the XC value, XC value, you can make it as inductive and capacitive. Okay, generally in case of FCTCR, this is the FCTCR circuit. In case of FCTCR circuit, the okay, in case of this FCTCR circuit, we take the inductance greater than the capacitance. So we can make purely inductive or purely capacitive depending on the switching. Because this current is varied, so that inductance is varied. So you will have either purely inductive or purely capacitive, or the combination that we change, because this reactance is changed. So by changing this reactance, we can change the reactance to either capacitive in nature, that means it supplies reactive power, or overall reactance may be inductive, so that it absorb the reactive power. So this way we can make inductive or capacitive in this FCTCR circuit. But whereas in TSR, TCR or TSC, either inductive or capacitive we are taking, but here combination of inductive capacitive, that means it can absorb or supply reactive power. So all these devices we are come under one category, that we take it as a static var compensator, SVC. SVC we are assuming. What is SVC? SVC is a shunt compensating device. Okay, static var compensator. It is connected to the transmission line via coupling transformer, and here we are taking number of devices, that is TSC, TCR, the TSR, fixed capacitor, fixed inductors, filters, all these things we can consider. Okay, and any two, combination of any two will be taken as SVC, which is capable of supplying reactive power or absorbing reactive power, like STATCOM, but it has limitations. Once you compare this SVC with the STATCOM, it has limitations. That limitations comparison we have seen. Okay, once again. Okay, so here we are taking TSC, TCR, TSR, TSC we are taking. So same circuits we draw here, and permanently switched capacitors, permanently switched inductors we connect, and filters. Filters are also, because number of filters generally will be tuned to a particular harmonic, and it will be placed to reduce that harmonic. For example, if third harmonic is dominating, we tune LC to that third harmonic value frequency 3 into F, and we place that LC value here, so that only for that voltage or current it will act as a short circuit path, so that it is absorbed by that uh, filter, and it won't affect the loads connected to the same transmission system. So that is the passive filter. So that is also taken in this SVC. Okay, because depending on the value of XLXC, that okay, XLXC, it has capability at fundamental frequency. Either XL is dominating or XC is dominating, so that it is capable of again compensating the reactive power as per this is SVC is concerned. That's why so filters are also taken in this static VAR compensator. Not only inductor, permanently switched inductor, permanently switched capacitor, TSR, uh, TCR, TSC, along with that one we consider. So overall, if you see that static VAR compensator, it has the capacity to compensate real power only. We don't talk about, sorry, reactive power. We don't talk about real power, because it won't supply, because no active elements are there. If you see the static VAR compensator, all are passive elements, just only switches and passive elements. So no active. Active means voltage sources you should have, like converters, voltage source converter or current source converters. We don't have any source in this static VAR compensator, all passive elements with the switches. So definitely the losses will be there, so that they draw the real power from the mains to compensate the losses. And never you have question of whether it is supplying real power or not. Only it will exchange the reactive power only. Remember, reactive power only. But both, that is positive, negative, or inductive reactive power, or capacitive reactive power, or it supply or absorb the reactive power. That you get in the case of SVC, static VAR compensator. But in the case of STATCOM, once you have a storage, I'm saying, okay, secondary storage will be there generally in the case of this STATCOM. Nowadays, the STATCOMs are coming with renewable energy sources on one side of the source, so that they have capability to exchange the real power also with the mains. So that you get in the case of STATCOM, but that is completely absent in the case of static VAR compensator, SVC. SVC, don't think that SVC is a different one. It is a combinations of whatever we have discussed these devices. That's all. So that is about the SVC. So today I will end the class at this point. Okay. Thank you very much for joining.